Hey, it's me, just editing the video here. I just wanted to let you know that, you see that one of the audio channels is completely blank. Yeah, apparently, this dumb idiot, if you pull this out slightly, just a little wee, just the tiniest little bit, the light stays on, so you think it's on, but it's not actually sending any information to the computer. So none of my audio got recorded. Luckily, Bryant's did, so he sounds better now. I don't have to use the camera audio for him anymore. Thank you for pointing that out. It did sound awful, by the way. But now you have to listen to me through the camera's audio. So, sorry. It's going to be like that for the next couple of videos. Also, this dumb idiot decided that its battery was going to blow a fuse. So now I can't use it outside of wall power. And this happened. Love and life.
Colonel.
You can hold them?
Yeah.
Oh my god. I'm gonna be getting my fucking frame. 3, 2, 1. Okay. Wow. First off, I want to start this by saying thank you. As of the recording of this, the Elden Ring video has 1,200 views. I never thought anything would get nearly that much attention. So from the bottom of my heart, a huge thank you to everyone that watched that. That genuinely made my day when I saw that. If I can make one request though, maybe spread the love to the other videos. Because right now it's sitting like Elden Ring, 1,200 views. All the videos around it sub 10.
I like the lightning one.
I love the lightning video. That one's my favorite one that we did.
Yeah, check that one out. Point somewhere.
Yeah.
Give me a place to click on.
All of the good videos are in a playlist called Caustic Talks.
Ooh.
So check out the other ones sometime.
Yeah.
They're the same style as the Elden Ring video, but other topics, like mostly science, and 2 of them are on ice hockey.
Yeah.
It's
Hockey.
cool. It's fun. Please watch them. But anyway, on to today's topic. I finished playing Outer Wilds on stream. I streamed it. I think it was like 3 or 4 streams I did of it. Fantastic game. I'm going to talk about that later though. Not right now. Today I want to talk about something else. Outer Wilds revolves a lot around the star of your solar system reaching the end of its life and going supernova.
What the hell is this? What the fuck? Oh my days. That's that's unfortunate. Okay, yep. I have all the flesh just fucking burned off my skin.
So, I wanted to make a video today about the life cycle of stars and the different types of supernova that there are.
It's like supernova, supernova. Yeah. I don't know what kind of supernovas there are. That's why I'm here. You're gonna tell me.
I'm gonna tell you.
I actually think I saw a thing about supernovas and how deadly they were based off of distance from Earth and light years. And it was like 90% of the 90% of the time I was like, it's far enough, don't worry about it. And then I was like, okay, now this is getting very scary. It went from like everything's chill to doomsday pretty fucking quick. You know that saying, you can run but you can't hide? You can hide, but you can't run from a supernova. Red dwarf. I like dwarves.
Rockin' Stone!
rock and stone. We're rich.
Okay, so all stars start their life as what is called a stellar nebula. And a stellar nebula is just a big pile of dust and gas floating around out in space. Now, through some reason, sometimes gravity, sometimes electrostatic forces, some of that stuff will clump together. And then that clump will start gathering more stuff and increasing the size of the clump. And then eventually that clump gets so big that the gravity it creates starts attracting more stuff into that clump. And then that clump of gas grows so much and so massive that the weight at the center of the clump gets strong enough to counteract the positive forces of protons repelling each other and causes atoms to start fusing together.
Oh, hell yeah.
And that is how a star is born. Fusion is a whole other topic. I'm not going to get on it now. Just know, for the purposes of this video, fusion is when two atoms, most notably two atom nuclei, fuse together into a heavier atom, which releases a ton of energy. Like a metric buttload of energy.
Yeah. Quick tangent. Do stars have gender reveals?
Boy, girl, non-binary.
Everything in between.
I think I got that backwards.
Boy. Did you just assume those stars' gender? Fucking dare you.
So at the core of the stellar nebula, it's formed in this massive clump of matter, and then the mass gets so big that it starts compressing itself so much that it starts nuclear fusion in the core of it.
Right.
And so the stars are so heavy that they're constantly trying to collapse on each other. They're so massive that their own weight is trying to collapse in on itself, and the only thing stopping them from collapsing is the energy produced by that nuclear fusion pushing back out on the gravity. So it's a constant tug of war between the compressive force of gravity and the pushing force of the nuclear fusion, keeping the star alive.
Right.
And so when stars form, that stellar nebula is mostly hydrogen with a little bit of helium. If you remember from our periodic table, those are the two lightest elements on the periodic table.
Yeah.
And also the two most abundant elements when the universe first formed and stars started popping out.
Yeah, and a bunch of elements got made from those fusing together. It's like 1 + 1 makes 2.
So
2 + 1 makes 3.
Stellar nebula can form mainly 3 different types of stars. There are more, as you can't really classify everything into neat little categories. But the 3 biggest groups are the dwarfs, most notably red dwarfs, the main series stars, which our sun is one of, and supergiants. We'll start with red dwarfs. Red dwarfs are tiny little guys. They're just little guys.
Just a little guy. Just a little guy.
They are actually small enough that convection currents are twirling around inside of red dwarfs.
Okay.
And those convection currents mean that the hydrogen that the red dwarf is fusing in its core is constantly getting swirled around. And the helium that is the byproduct gets taken up to the surface and fresh hydrogen gets brought in.
Oh, okay.
This vastly increases the lifespan of red dwarf stars. We have not seen a single red dwarf star die yet.
So
the universe is over 14 billion years old, and we haven't seen a single red dwarf die. I think it's theorized that they can live for trillions of years.
Hell yeah.
Like, the universe is barely like a tenth of how long a red dwarf can live for right now. But in the eventuality that a red dwarf star does use up its supply of hydrogen, it can start fusing helium.
Okay.
doesn't release as much energy as fusing hydrogen, but it still does release a crap ton of energy.
Right.
However, when a red dwarf star runs out of sufficient helium to fuse, it will die off.
Oh.
Now, a red dwarf is actually not massive enough to create a supernova per se. It'll do this thing where the core is left behind, and there's just this radiated stellar material that kind of just floats off. So when a star runs out of material to fuse, it can't resist the push of its gravity anymore, so it kind of collapses. But there's a point where it can't collapse anymore. It gets so dense that it won't collapse further past that point, and most of the material will then just rebound off the core and explode out. That's what this radiative stellar material is. It's the stuff that the red dwarf was made of, bouncing off the core and radiating out into space.
I heard there was a thing where it might be red dwarfs. When they die off, they're going to leave behind just like diamonds, just like pure diamonds. Or is that a different thing?
I might. No, I'll talk about that right now. Stars can create carbon.
Right.
It's a part of their fusion chain.
Yeah.
Red dwarfs don't get there, but main series and supergiants do. They are heavy enough to fuse elements into carbon. However, they won't stop at carbon. So, in order to make diamonds, you need carbon, because diamonds are made of carbon.
Right.
But a star will fuse past carbon.
Yeah.
Stars like main series and supergiants stop at iron, because you can't get any energy out of fusing iron. You put in too much energy, more energy than you get out when you fuse iron.
And then you get the push and pull kind of fails.
So iron is the stopping point for fusion,
Right.
and so when stars reach iron, that's when they die.
Right.
So they just breeze right past carbon. Any carbon that is made in the core of a star theoretically could maybe be considered diamonds if it wasn't so hot that all bonds between carbon atoms
blew apart.
dissipates.
Yeah. Okay. I don't know where I saw that, but
I don't know
some
either.
kind of size thing. Might have been fake. Might have just been one of those clickbait Facebook ads. Our professionalism is astounding.
Yes, it is. So after that stellar material radiates off of a red dwarf's core, what you are left with at the end is basically the corpse of a star.
That's metal as hell.
Yes, it is. It's what's called a white dwarf.
Oh, okay.
If a red dwarf is sufficiently is of a certain mass, when it kind of dies off, it could turn into what's called a brown dwarf, which is a star that's not really a star. It's like a clump of glass, a clump of gas, like a slightly larger than Jupiter, that can do nuclear fusion, but doesn't consistently do it enough to be considered a star. So it's a brown dwarf star. Something that can do and does do fusion, but very slowly and sporadically. A red dwarf can become that, but usually they just become white dwarfs.
White dwarfs, aka Brunkles, aka
aka. And that is the last death throes of a star as a white dwarf. All of the white dwarfs are still pretty luminous because they still are stars, but all of their luminosity comes from the intense heat of the core being compressed so much. They can still last for a long time with the light they illuminate, but once you get to a white dwarf, that's pretty much it.
And that's just the core of the red dwarf left behind, and the compression and the heat.
So, main series stars. Our sun.
Hell yeah.
Big boy.
Big boy. The light of my life.
These guys are... So, the masses of stars are measured in what's called stellar masses. And that's basically just comparing stars to our own sun. Our sun is one stellar mass. Dwarfs are obviously less than that. Like, I think they're like 0.1 stellar masses around there, I think. I'm not sure. So main series stars are like 0.8 to 2 stellar masses or something. Again, I'm not sure on the specific numbers. But yeah, so these big boys, our sun currently is still fusing hydrogen. Fusing hydrogen into helium. unlike red dwarfs, they don't have convection mixing because they're too big for that to happen.
They still have like a convection zone.
They have a convection,
But it's not the same.
mixing zone,
Yeah.
but it's not the same as
Through the whole
The red
star.
dwarf is an entire convection zone.
Yeah.
So it actually won't burn through its entire source of hydrogen before it starts fusing helium. And when it starts fusing helium is when it will inflate and kill us all. Because when a main series star starts fusing helium, it will inflate into a red giant star.
And they're saying it's gonna what? At least take up Mars, right?
Yeah, I'm pretty sure estimates
March
say that
past
when
Mars.
our sun inflates to a red giant, the radius will increase out to Mars's orbit.
Yeah.
So we'll be sufficiently dead.
It's gonna be inflation and then vor, and nobody likes either one.
But that is going to be best estimate like hundreds of millions, if not a billion years from now.
Yeah.
So
Not
we
a-
don't have to worry about
Oh,
it. We probably won't. Humans probably won't even be here by then. We'll have fucking killed ourselves off by global warming or something.
Yeah.
So it inflates to a red giant and starts fusing helium, and this is where we get to talk about the fusion chain. Because as we mentioned with carbon, helium it continues to use fusion as its fused source past helium. I believe helium fuses into carbon,
Probably carbon.
which then fuses into oxygen or nitrogen, and then they fuse into a few other things, all the way, like they fuse into silicon,
Yeah.
and then they stop at iron. Iron is a very stable, it's probably the most stable element. If you remember from the periodic table, it's in the first row of transition metals. It is an incredibly stable element because for some reason...
D5, half-filled shell.
Yeah, something... Well, actually, electrons aren't even a point in this because when you're considering fusion, electrons are just blown off. It's just the nucleuses that are interacting. Because iron is the stopping point for both fusion...
Call me an electron because I'm getting blown off by these hoes. Sorry.
Iron is the stopping point for both fusion and fission. Fission is basically the opposite of fusion. Instead of combining two nuclei, you're splitting a heavy nucleus into two smaller ones, which releases a lot of energy.
Yeah.
It's what we use in nuclear reactors and nuclear bombs. And for some reason, iron is the stopping point where you can't get any more energy out for both processes. Both fusion and fission lead to iron.
That's crazy.
Yeah. So once a red giant star gets to iron and it amasses what's the word? Sufficient iron core that it can't actually produce any more fusion. Because like once an iron core starts, it can still fuse material around it to keep pushing out. But once it reaches a sufficiently sized iron core, fusion just stops. And that's when
You're cut off.
and that's when the collapse happens. Everything shrinks back down and then rebounds off the core. And however, it's not as violent as you may think because main series stars do the same thing as red dwarfs.
Huh.
They just rebound matter off as a stellar nebula.
Cool.
And then turn into a white dwarf.
Man, so when it inflates and kills us all, we won't even get a cool explosion out of it?
No, we won't. I mean, okay.
Not with a boom.
To put things into
whimper.
perspective, this stellar matter getting radiated off from bouncing off the core
Yeah.
is still incredibly powerful. Like, we're still talking about star matter getting flown
It'll
off
just
at
strip
incredible
atmosphere,
velocities.
rip shit apart.
Like it'll strip atmospheres, give living, just obliterate,
Just
incinerate
irradiate
everything, vaporize oceans. Anything left for whatever reason that could have survived will now have cancer. The intense radiation. Like this is still a very destructive process, even though I say it's
Not
more
as
mundane
violent.
for stars.
Yeah.
And that is because we are comparing it to the next one of supergiants.
Yeah.
Supergiants just are the whole shebang.
They're the drama queen.
When a supergiant dies, because here's the thing. Here's the funny thing. As you make a star heavier,
Right.
you shorten its lifespan. Red dwarfs have a lifespan in the trillions. Main series have lifespans in the billions. Supergiants have lifespans in the hundreds of millions.
They're morbidly thick.
They live hard and die fast.
Hell yeah.
Because they are super bright. Like, intensely bright.
They're the rock stars.
They are the rock stars. And then they just
like the
explode
rock
in the
stars.
most majestic way possible. When you think of supernova with a massive explosion that destroys everything around it, that's a supergiant supernova.
Oh, okay.
So a supergiant goes supernova when all the matter gets yeeted off of it because it bounces off the core. And then, depending on the mass of the supergiant, it could turn into one of two things.
Okay.
I believe if the stellar mass is less than 10 solar masses, it'll turn into what's called a neutron star.
Oh, I've heard of those.
Yeah. So a
thought this
neutron
was a
star is an incredibly small, on the cosmic scale, incredibly dense star. Just like the white dwarf, all the light that comes off the neutron star isn't from fusion, but from how incredibly hot it is. Because you've taken the iron core of the supergiant. Imagine this. A supergiant that's 10 times our sun. Its core gets compressed into a ball the size of New York State.
Jesus Christ.
It is incredibly small for a star, incredibly dense. And the reason they're called neutron stars, and this is very cool, is because the crust of the star is what's left of its iron core. It's a very thin, very dense crust of iron on the outside of the star. On the inside of the star is a soup of neutron matter, where all of the protons and electrons that were inside the core have fused into neutrons.
Oh.
And
Which
then,
is like
then
most
all,
of the mass.
Yeah, all of the mass that was in the core has become neutrons. And now it's this gelatinous, superfluid mess soup of just neutrons. And if you took a teaspoon of it, it would weigh more than Mount Everest.
Jesus Christ. Just like me. Incredibly small, incredibly dense, incredibly hot.
And
The
so
trifecta.
if this thing is spinning really fast, which it probably is,
spin real fast.
because it's the compressed core of a star, which is already spinning, and so since it gets smaller, it's going to start spinning quicker.
Yeah.
It's going to
Conservation
generate
mode,
a
whatever.
massive magnetic field, and these are called magnetars, where there's this big radiation pulse out the north and south poles of these stars that are orbiting like a lighthouse.
Cool.
They're very cool, and scientists have been able to determine that these are very regular rotations, and have been able to use that to determine the distances in space.
Oh, okay. Because you can see like how long it takes for it to come around or something.
Yeah.
Right?
The last thing we're going to talk about. If a supergiant is over 10 solar masses, I think it is. It might be more though.
There's some number that determines this.
Some number that determines this. When the star collapses, its core is so incredibly massive and shrinks at such a rapid pace that the collapse goes on a breakaway. It just keeps collapsing and keeps collapsing until the core becomes the mass of a star in the point the size of a pencil tip. And that is what we call a singularity or a black hole. A point in space of almost infinite density that not even light can escape from.
Yeah.
These are just, when physics goes to the extreme, it breaks down. And you've seen the popular depiction of black holes with like the ring around it and then the ring on top of it.
Yeah.
That is actually very interesting. It's just the ring around it. There's only one single ring.
Oh.
The ring you see on the top and bottom of it is the light from the back of the black hole curving around it so you can see the ring on the other side of it that you shouldn't be able to see.
Oh, okay.
Yeah.
Yeah. It like it kind of like you drew it pretty well. It like almost like folds up.
Yeah, it fucks.
Like curves.
Black holes fuck with everything.
When she's so thick, you can see the back from the front. Hey.
Like the first black holes that were discovered, the astronomers thought they had made a mistake because there's just a point in space where there's just nothing.
Yeah.
They're just seeing nothing there. There should be something there, but there's nothing.
Yeah.
And then they later found out that it was that the light around that point of nothing was being warped and bended. And they're like, why is that happening?
Did somebody get something on the lens?
And then eventually, I can't remember if it was Einstein. It was probably someone before him.
Some great.
But some incredible scientists, like Einstein and Stephen Hawking, were very influential when it comes to black holes in the scientific community. But I'm pretty sure black holes were discovered before Einstein, I think.
Yeah.
But anyway, someone just realized, like, hey, maybe that's actually a stellar body. Yeah, so
there's got to be something out there.
Yeah. So supergiant can turn into a neutron star or a black hole if they're on either side of a certain threshold of solar masses. Another thing about black holes, this is very interesting, is at the center of, I think, every galaxy, but it might not be every, it might just be most. At the center of most galaxies, there is what is called a supermassive black hole.
Yeah.
And these things are incredibly large.
Oh no.
Like, this is a black hole. A thing that is near infinite density. That should be a singularity. The size of a star.
Jesus Christ.
It's like, how did that thing form?
You can't even fathom how
You
much
have
mass.
You have the remnants of a
Density.
collapsed core.
Yeah.
That's as big as a star.
I mean, as black holes eat and pull in matter and light and everything else, don't they grow in size a little bit?
A little bit. Very small amount, though.
So these could just be really, really old black holes, right?
But that's the thing, is scientists have thought of that.
Yeah.
And they measured that even if a black hole was eating other black holes, it should not have been able to get that big in the time span of the universe. The universe is too young for it to be that large from that method.
I wonder if we just had like bigger stars.
That is
like
an
uber giant.
that is actually the theory.
Yeah.
That when the universe was younger,
There's
and
just so
everything was
much stellar
more
nebula, stellar
packed
mass
together, because like the universe is expanding.
Right.
Everything is moving away from each other. So when the universe was very young, everything was much more closely compacted together. So the theory is we were able to get incredibly massive stars that we would never be able to get,
And then
that had black holes at their core.
oh god.
Chris Gassat, in a nutshell, did a cool video on it. It's called Black Hole Stars, where you have a star with a black hole at its core. It is
The fuck.
dope, and it is hugely, way more massive than anything we know of right now, theoretically.
Yeah.
There's no definitive proof of this, because obviously they don't exist right now. But it is a theory as to how we got these massive black holes.
Yeah. And like those would have had to been pretty short lived. I mean, they've got a fucking black hole in the center of them, pulling everything in and just eating it.
Well, here's the thing about a black hole.
Also, like,
it's a black hole isn't necessarily like a vacuum. Vacuum cleaner.
you just can't get out of it.
It doesn't necessarily pull stuff in. Because if you have a planet that's orbiting a star, and that star turns into a black hole but doesn't blow the planets away, they'll just keep orbiting the black hole. Because that's the same mass.
Yeah.
So since the mass hasn't changed and
Gravity
the
won't
orbit,
change.
and the orbit hasn't changed, gravity hasn't changed.
Yeah.
So the planet will just keep orbiting that black hole as if nothing happened. The only time black
Somebody
holes,
turn the lights out.
yeah, pretty much. The only time a black hole really eats something is if something flies too close to it. Because
Right.
black holes have this thing called an event horizon, which is a certain point in space outside of the black hole where not even light can escape it. In order to escape the gravitational pull of the black hole, you need to go faster than light, which requires infinite energy.
Yeah.
But if you don't cross the event horizon,
You're fine.
you can totally just go away.
Oh, cool.
Yeah.
They're not so scary.
And the rings around black holes are what's called accretion disks.
Okay.
That's basically just matter stuck in orbit around the black hole that's moving so fast that it starts glowing hot. It gets glowing or like past red hot into orange hot and just starts glowing because of how fast it's moving. And there's this thing, I don't know if I want to get into it because it could deserve its own video. Do you know what Hawking radiation is?
A little bit. I've heard about it. I
Yeah,
know.
so basically in the universe, you have massless, formless energy, right?
Pure energy.
Yeah, literally pure energy. And then that energy, what happens is it can spontaneously form into matter
Yeah.
and equal parts antimatter.
Okay.
And normally when this happens, the matter and antimatter are right next to each other, and so they
Just like-
touch each other and obliterate, go back into the exact same amount of massless energy.
Oh, cool.
However, if this happens on the event horizon of a black hole, so that one of the particles falls into the black hole and one of the particles escapes,
Right.
that black hole loses energy, and so it loses mass.
Oh, okay.
And so slowly, and this was discovered by Stephen Hawking. That's why it's called Hawking radiation.
Right.
Slowly, this black hole will radiate out these particles and will slowly lose mass until it dies.
Yeah.
And the smaller, conversely to the stars, where the bigger it is, the smaller its lifespan is. With black holes, the smaller it is, the shorter its lifespan is. So a smaller black hole is just spewing off Hawking radiation, whereas a giant, a supermassive black hole is just trickling it off, just living its life. And then when they reach a certain point where they've released enough, they just fucking explode.
Hell yeah! More explosions.
Like, I don't know how a black hole goes boom, but it do.
It's called Taco Bell, my friend. That's what makes my black hole go boom.
That's a brown hole.
Brown hole. My bad.
But yeah, so that's stars and supernova.
I heard. I mean, I hear it. Maybe I just make this shit up. Maybe I hear it and I don't really like look as deeply into it as I should. But at least I don't like accept it as fact. But I heard that like it'd be a pretty fucked up death to fall into a black hole.
Oh,
because like you just get spaghetti-ified
Yeah.
at
so
the event horizon.
because the black hole is so small but so massive,
Yeah.
the differences between gravitational pull. So with any large mass that has gravity, like the Earth or the Sun, its gravitational pull is dependent on how far away you are from the core of that object.
Right.
With a black hole, because it's so massive in such a small space, that difference is astronomical. So if you're falling into a black hole, and say the black hole is right, let's use the one I've already drawn. And then, so you're falling towards that black hole. Your legs are here, your head's up there, there you are. Just being a man out in space, falling into
Spaceman.
a black hole. Your legs, you are, let's say 6 feet tall.
Yeah.
Because your feet are 6 feet closer to the black hole than your head is, your feet experience 10 times more gravitational pull than your head does. So your body just gets yoink, and you just stretch out and spaghettify, like you said, as you fall into the black hole. And the process is called spaghettification, as matter just gets infinitely stretched into the black hole.
It's not as fun as it sounds.
No.
I love spaghetti, but
due to the way space works, because black holes are weird, if someone was observing you, they'd see you falling into the black hole, you'd pass the event horizon and just stop, and then slowly fade away. Because all the light that's getting reflected off you is just falling into the black hole. So they just see you stop and then fade.
Yeah, and you like you die, but your like remnant stays there for a long fucking time too, right? Because time gets all timey-wimey because of gravity.
Black holes, man.
Yeah.
But yeah, so that is stars, supernova, and the lifespan, and all different kinds of stuff, and a little bit on the black holes.
Yeah.
Do you have any questions?
How do you get your hair so nice?
I use separate shampoo and conditioner.
No!
Don't use the two in one conditioner. It's actually pretty bad for your hair.
I actually use a bar of soap on my hair.
Yeah, like those men's soap that's like shampoo, conditioner, and body wash all
and motor oil.
The worst thing and motor oil. It's like the worst thing you can use for your hair.
Yeah. All right. Well, that answers my question of the week.
Okay. So I'm not a huge fan of plugs and calls to action. So I'm going to say this once and never again. If you like the content that I'm making and the videos that I'm doing, if you like it, hit the like button, subscribe, whatever. That's going to be the last time I'm ever going to say that.
Hit the notification Taco Bell. Blow up your brown hole.
But something I will say, probably, maybe, if you have any questions, please absolutely leave a comment down below. I would love to answer any questions you may have.
Oh, hell yeah.
Also, if I got something wrong, because I probably did, or you think there's something that I missed that you think is people should know about, please leave that comment down below as well.
Yeah.
I will pin it to the top.
Hell yeah.
I will pin any corrections and anything that I missed to the top so people can see.
That's all part of science.
It is all part of science. We are all learning from each other.
Exactly.
Thank you for watching.